8.8 Properties of Buffers. So the outcome is I can explain the relationship between the ability of a buffer to stabilize pH and the reactions that occur when an acid or base is added to a buffer solution. So you're going to start out with this Khan Academy video, and then there are some questions to answer. So go ahead and pause this video and switch over to the Khan Academy video. So we're going to complete this diagram here. So this diagram is showing us our buffer in the middle, and it's showing us what happens to that buffer when we add an acid or when we add a base to the buffer. So first, let's start by counting the components of our buffer here. So I have 1, 2, 3, 4, 5 HAs, 1, 2, 3, 4, 5 A minuses. So right now this is an equimolar buffer, and the pH would just be equal to the pKa here. Now every time you add a little bit of base to this buffer, notice that if we go in this direction, which is adding a base, we have one less HA and one more A minus. So one of those HAs has been converted into A minus. So for this reaction, we're going to get H2O. So these guys combine to give us water, and then we'll have A minus floating around. If we go in the opposite direction, if I were to add acid to my buffer here, then I would end up with one less A minus because that base would have accepted an H plus from H3O plus. So I would have one more HA and one less A minus. A buffer system is created from acetic acid and sodium acetate. Write two equations showing how this buffer would react with added acid and added base. So when we add sodium acetate into water, we're going to get Na+. Na+ is a neutral ion, so it would never be part of a buffer. And then we have acetate minus, which is a weak base itself. So when we add sodium acetate, we're actually forming acetate in solution, and we also have acetic acid. So if I were to take my acetate and react it with acid, then the acetate would accept an H+, forming acetic acid. Now it's important that this acid is a weak acid. That means that it's not going to dissociate back into H+ and acetate minus to a large extent. It's mostly going to store that H+ in the form of acetic acid. On the other hand, if you have acetate, acetic acid, and reacts with base, that base is going to accept an H+, again forming H2O, and will form this time acetate. So there are some components in this buffer from the sodium acetate. That acetate will neutralize any added acid, whereas the acetic acid would neutralize any added base. Use the diagram to explain why buffers maintain a specific pH when an acid or base is added. So because buffers contain one component that neutralizes acid and one component that neutralizes base, the pH is going to be kept relatively constant until eventually those buffer components run out. So predict what would happen if an acid or base keeps on being added to the buffer. At what point will the buffer no longer function? So if you keep adding acid to your buffer, eventually all of that basic component is going to be neutralized. So when you add that next drop of acid, there's nothing to neutralize it, and your pH will drop. Likewise, we see the same thing if we're adding a base. So every time you add a drop of base, a little bit of it gets neutralized by the acid present in the buffer, the weak acid species in the buffer. And over time, you eventually use up all of that weak acid. So when you put that next drop of base in, there's nothing present in solution that's going to neutralize that, and so your pH is going to suddenly increase. So there's a couple of reflection questions for you. Explain why a strong acid cannot be used as a buffer component, and how does the amount of added acid or base to a buffer that a buffer can withstand, how is that related to the amount of weak acid/weak base present, to the amount of those buffer components?